So good afternoon. My name is Filippo Sugianto, and today me and my teammates are gonna present of our final team project in thermofluid system and engineering. So for the objectives of this project is to create a steam generator with a maximum dimension of 1.5 meters times 1.5 meters, which can deliver 25 kilograms per hour of saturated steam at 150 degrees Celsius. And there must be components of preheater, steam drum, and insulation. The optimization, we need to minimize the fuel consumption since the maximum budget of $200 per month for fuel, and we must choose a suitable fuel source, either LPG or biomass. And we must ensure that the startup period is 20 minutes or less and below 6 bar of pressure operation. To model this, we use software for modeling, and we need to see the thermal behaviors for startup, steady state, and in between. Abstract. So uh, the need for the steam generator is for a small scale food processing facility, which needs a steam for 25 with a mass flow rate of 25 kilograms per hour at 150 degrees Celsius, which operates 6 hours per day, and the system must fit in the specified 1.5 meters times 1.5 meter space. The fuel is either LPG or biomass, and it must be a fuel efficient and a reliable system. For this modeling and simulation, we simulate under various load conditions, such as the startup period and the steady operating period. We optimize the insulation to reduce the heat loss, and based on evaluations, the final design must meet the safety and operational standards. Design of the system. The key subsystems in our design are economizer or preheater, which utilizes straight tube cross flow as a heat exchanger to utilize the wasted heat from the furnace from the LPG combustion, and then to heat the water before coming to the furnace. The furnace and boiler are designed consists of a 150-liter tank to store the water, with 6 centrally located tubes to ensure even heating of the water. The steam drum, our steam drum is located next to the furnace, which its function is to store the steam once generated by the furnace. The design follows the standard of ASME Section 7. The piping is utilized to transfer the heat from the steam from the surface to the steam, as well as another line transferring the heat from the furnace to the economizer. This is the CAD modeling of the boiler and furnace. Now for the fuel force, this is the either choice is LPG or biomass. LPG have a higher energy content per kilogram, but biomass requires a large storage areas that are that need to be dry. LPG storage tanks are more compact and easy to transport, as we can see on the left. And LPG have a cleaner combustion with less emissions due to the low content of ash in the fuel. Biomass combustion requires cleaning of tubes. That is because biomass has a large ash content, and biomass is cheaper per kilogram in comparison to LPG. As we can see that there are more advantages of using LPG, thus LPG is chosen as our suitable fuel source. So this is our chosen design, as we can see on the middle picture, which is an LPG furnace with 6 centrally positioned tubes on the right that can efficiently heat the water due to the large surface area from the tubes. First, the room temperature is routed to the preheater before entering furnace, so this is the startup procedure. Combustion begins once only the furnace tank is filled, making initial LPG consumption slightly higher during the startup procedure because of the larger temperature difference. Waste heat from the combustion is recovered by the preheater. So the waste heat coming from the furnace will be transferred through through piping through the preheater or the economizer. Then the steam generated will be stored in the steam drum by piping. So our design is compact and clean. The LPG has minimal contents of ash and then high efficiency. So because of the six centrally placed tubes in the furnace, which can evenly heat the water and control combustion, LPG allows precise and automated control for safety use of the system, following the safety code of NFPA 86. So there will be less risks of uh, of negligence. So the materials used in this udah ya so udah cowok.
Good morning. Hello. My name is Ariya Cittaparami, 131228183. So in this thermofluid system and engineering final project, I made the economizer, the preheater. Let's go back, shall we? So the preheater or the economizer is a key component in our steam generator system. Its purpose is to utilize residual heat from the flue gas to preheat the feed water before it enters the boiler. This increases overall system efficiency by reducing the thermal load on the main furnace. Now, for the design itself, we use these kinds of materials because they are a good heat conductivity and they are also have a good strong stress for thermal. Now, this is the simulation for the preheater. This is the temperature graph of the on the left side here. This is the temperature graph of the flue gas. As you can see, this is the inlet. As the gas goes in, it starts to spread, and then it goes out. And this is what it looks like from the drum. And this coil itself is the feed water. As you can see, we can get a maximum temperature of 350 degrees Celsius for the outer walls of the economizer, while the inner tubes have a maximum temperature of 100 degrees Celsius. Now, this is the simulation for the preheater. As you can see from the ANSYS fluent setup, I calculate the data and I got for the mass flow rate for the gas inlet is about 0.00833 kilogram per second. That is about 29 kilogram per hour. And for the water inlet and water outlet, they are basically the same. As you can see, it is quite constant. They are at about 0.00694 kilogram per second, and that is about 25 kilogram per second, at 25 kilogram per hour. And for the temperature, as you can see here, the water inlet itself is 25 degrees Celsius. But then as it goes out from the preheater, you can see that it reached a temperature of about 51 degrees Celsius. Okay, next to Dolfa.
Okay, let's now begin to the process flow diagram of our system. We built this using Aspen HYSYS. So the first thing we have to know is all the components that useful in our process, in our analysis. So the first one is the pump, the second one is preheater or economizer, the third one is boiler, and the fourth one is the steam drum. It's like this: the tap water, which have temperature 25 degrees Celsius, pressure about 150 kilopascal, and mass flow 25 kilogram per hour, will pass through the pump and pressurize until the pressure reach 750 kilopascal. Why we have to do this? Because as we already studied in the thermodynamics, that when we want to achieve 150 degrees Celsius as steam, saturated steam, we have to get the liquid that we use to be in the pressure region of 150 degrees Celsius, steam saturated. After being pressurized, the tap water will go through the preheater and get heating up by absorb the heat from the hot flue gas from the boiler. So the process is like this: the tap water will go through the preheater and went through the coil tube coil tube configuration, and the hot flue gas from the boiler will flow outside the coil, which have the water flowing inside that. So the heat from hot flue gas will be absorbed by the tap water and then got the temperature higher. In our system itself, we divide into two cycle. The first one is the transient, and the second one is the steady. What is the difference? The transient one is when the starting up condition, which is the preheater or the hot flue gas, is still not flow into this preheater, so there is no increasing temperature of tap water passing through the preheater. So the 25 degrees Celsius tap water will stay as 25 degrees Celsius, and when inside to the boiler. In the boiler, the water will fill up until reaching a certain volume, and then the inlet of the boiler will close. So the system in the transient is like you boiling up the water in the pan. Yeah, so there's no water coming in and there's no steam coming out until reaching the 150 degrees Celsius. After the process reaching 150, the hot gas is already flowing through the preheat. So in the steady, the inlet the inlet water will have higher pressure, which is in our system we choose 51.77 degrees Celsius. We got that from the simulation. So yeah, so in the steady we just have to increase the temperature from 51.77 until 150 degrees Celsius. After reaching 150, there is a saturated steam coming out from the boiler and go through the steam drum, and is ready to be used for our blanching application or other. So for the properties of each fluid and each component is already shown in the table in this picture. So let's go to the component geometry of each component. So the first one is the boiler and furnace. As you can see, the furnace is the region where the combustion happen, and in this case, it is inside the boiler. The boiler itself is the shell that's surrounding the furnace. And so the coil preheater configuration is like the picture here. So actually, the mean diameter is 150 millimeter that we already built. So pipe diameter that the water will flow inside is about 29.70. And the third one is for the steam drum geometry. The steam drum is just for collecting the steam coming out from the boiler, and it acts as a separator to the steam and the water coming out. So the diameter is like that in the picture. And the last one is the piping. The piping is quite crucial because it will transfer all the fluid between the component, the heat transfer, the flue gas. Yeah, so it's like a connecting. Without them, we cannot achieve loop of our system. So let's begin to discussing about the simulation for boiling water in the starting condition cycle. So we actually had already doing the simulation in ANSYS for the simulation for the starting condition in the boiling water. So in the left picture, this is actually a contact region water domain with the heating wall. So just the surface of contact to the heating wall. And I have to mention that in the simulation we use the mixture in the multi-phase of the setting. So yeah, the mixture consists of water, liquid, and water vapor. But somehow, because the water is static, there's no water coming in and there's no water coming out. Somehow the simulation doesn't show that the surface of the contact within contact region water domain with the heating wall is have a increasing temperature. So it just weird for me, and we didn't know how to solve this. We didn't know what's the problem because we follow the instruction in the YouTube, but somehow there is a maximum temperature about 700 that located actually in the top of this picture. Yeah, so it's like in the flue gas temperature out region. And after get this, we try to find another contour. So yeah, this is the heat distribution of the static water domain that we see from the outside of the static water domain. Yeah. So the temperature distribution in this surface is quite confusing because I don't know. Our guess is because there is a mixture. So the lower temperature is the steam, and the red red color is the water side. So yeah, it's like the boiling. There's a bubble when you boil up the water. So I don't know. I don't know that this simulation for the starting condition is successful. The next one, after doing that, we do the simulation for boiling water. So after getting the that result in the starting condition simulation in the boiling water, we proceed to the steady condition. In the steady condition, it's successfully simulated that all the picture shows that the outlet temperature of the boiler is successfully reaching 150 degrees Celsius as mentioned in our requirement in our design. And the inlet itself is the same as the inlet from the preheater, which is about 52 degrees Celsius. In the very left picture, we can see that this is the heat. This is the temperature gradient in the contact between the surface of the water domain to the furnace. So in the middle picture, we can see that for the top, which is the outlet of the flue gas, is reaching about 500.5 degrees Celsius. And in the very right picture, it shows that boiler cell is the outer boiler that surrounding the water domain. Yeah, so in the simulation, we assume it to have zero heat flux. So yeah, there's no temperature gradient in that region.